Okay, let's talk about the Beer-Lambert law. When you have a solution that contains some concentration of solute in it, you can determine the concentration of that solute by passing light through it. And the idea is that there's some intensity of light that you begin with. But after passing that light source through your solution, the solute present in it absorbs some of that light. And so what comes out has lower intensity. And an instrument can actually measure the ratio of the outgoing intensity of light versus the incoming intensity of light. And it turns out that if you take the negative log of this ratio, you get relatively simple values to deal with. Values that range from 0 up to about 2 or 3. So relatively small values, but it's technically a logarithmic scale. Now, what you get out of this is a relationship between the absorbance. So the negative log of the ratio of the intensities is what we call the absorbance. And the absorbance of a sample turns out to be linearly correlated to the concentration of the sample. That means that as you concentrate a solution more and more, so you have more solid present in it, the absorbance keeps going up, up, and up. And this is what we call the Beer-Lambert law, represented here by this equation, where A stands for the absorbance, C stands for the concentration, L is the path length in centimeters, and specifically that's the length of this cuvette that holds the volume of the solution. And then epsilon is known as the molar absorptivity constant if the concentration is molarity. If the concentration is something else, and this is simply the absorptivity constant. All right, now when you look at a graph, an absorbance versus concentration graph, absorbance represents the y and concentration represents the x. So epsilon times L automatically becomes the slope of this line. And as long as the path length is equal to 1 centimeter, it isn't always 1 centimeter, but unless you're told something else in regards to the value of the path length, you can assume it is 1 centimeter. But just make sure to read the entire problem to know whether you're dealing with a 1 centimeter path length cuvette or not. So in other words, out of the slope, you can determine the molar absorptivity constant. So that's the power of the Beer-Lambert plot. Another thing that I want to point out right now is that graphs of absorbance versus concentration, also known as the Beer-Lambert plot, is best when the absorbance lies within 0.1 and 1. When the values are much less than 0.1 or much greater than 1, you get into situations where there is no linear correlation between the absorbance and the concentration. And in the case of higher values of absorbance, the reason why that happens is because if the sample becomes very concentrated and very opaque, then it almost behaves like a reflective surface. And so some of the intensity of light is not being decreased as a result of absorbance, but it's actually being decreased as a result of refraction. And you don't really know how much the solution is refracting because you don't even know what the concentration is. So you have no way of really knowing what the actual concentration would be at their high values of absorbance. And that's why you want to keep the range within 0.1 and 1. Now, in terms of instrumentation, there is a lot of UV-based instruments out there. Some a lot bigger than others, some a lot more sensitive than others. But one thing that they all share in common is that you do have to have solutions that you're going to measure the intensity of light coming out of it as you shine light through the cuvettes. And in this little schematic, what I'm showing is not a definitive view of what's inside the machine, because depending on how the machine was made, this may look different. But typically, you will have a lamp, which is either a tungsten lamp or deuterium lamp, or a duet of tungsten with deuterium. Tungsten ensures that you are shooting the entire visible spectrum, whereas the deuterium lamp ensures that you have ultraviolet rays of light passing through. So then what happens is that you shine the light onto a mirror that bounces the light to a grating. And the grating is mechanical, so it can actually rotate on its axis. And the beauty of the grating is that there is an angle of reflection that mathematically matches the wavelength of the light source to this angle. So by rotating this grating to very specific angles, you can selectively determine which rate of light is going to make it pass slit number 2. And this slit is what ultimately leads to the light that you shine onto your sample. Depending on the machine you have, you may have two cuvette holders, one for a reference, which is the solvent, and the other one for the sample, or you may have to first add the reference and then the sample and then subtract from there on out. But really what happens is that the light goes through the sample um, and then gets redirected to a second grating that eventually makes it into a photomultiplier tube that converts this light source, this photon of light, into an analog signal that your computer reads out as the absorbance. All right, now a typical problem that you will see involving the Beer-Lambert plot is as follows. You will be told that there is an absorbance. Okay, so this sample of cobalt 2 chloride has an absorbance of 0.220. Now that's the value of A. This absorbance happens at a wavelength of 515 nanometers. Now this is actually a value given for reference, but you actually don't use at all in the calculation. This is meant to tell the experimenter, somebody who works in the lab, okay, you gotta set up your instrument to this wavelength of light, otherwise, you'll be looking at different things altogether. But you can use this data to find the concentration. And what you see right here is a table of concentration of cobalt 2 chloride versus absorbance. So what we do is we plot absorbance on the y and the concentration on the x in a plot using either Excel or Logger Pro. So what you can see right here is that concentration less than 0.001, or in other words, less than 1 times 10 to negative 4, which will correspond to the values here on the bottom of the table. And then we have three other values that are greater than 0.001, and you can see that in the graph itself. You have the three data points greater than 0.0001, and then you have three that are less, which is exactly what the table shows right here. All right, so we have absorbance on the y and concentration on the x. So you plot this and you get the linear fit equation, which in this case happens to be 931.1x minus 0.00074. So two things that I want you to notice. First thing is that the y-intercept is not exactly 0 as the Beer-Lambert law tells us, but it is actually kind of close to it. It's 0.00074. That's not that far off from being 0 altogether. But what's going to happen is that when you do make plots of the Beer-Lambert law, you will have a y-intercept, and you will need to use that linear fit equation altogether to solve for Beer-Lambert plot problems. But one thing that we know is that absorbance equals epsilon times C times L, where C is the concentration. This also means that epsilon and L represent the slope of this line. And right now, based on the equation, we know that the slope is 931.1. So epsilon times L has to equal 931.1. And in the data right here, nothing has been said about L. So we can assume that L equals 1. But in other cases, you may be told that L equals some other value, in which case you will have to plug in the value of L into the equation and then solve for epsilon. But here, the path length will be assumed to be 1 centimeter. And what that means is that epsilon equals 931.1. So this is how you find the absorptivity constant value. Now, to find the actual concentration of the unknown sample, it's best that you do not revert back to the regular Beer-Lambert law, but rather use the linear fit equation that we found here from the graph. So instead of just using 931 for epsilon and 1 for L and solving for C, we're going to use 931.1x minus 0.0074 to solve for the concentration. And all we need to do now is plug in the value of the absorbance, which is 0.220. Now, one thing that I've seen people do before as mistakes, and hopefully you won't, is that they will plug in the wavelength for the absorbance. And that's a huge red flag because, as I told you in the previous slide, absorbance has very small values. In fact, values above 1 are already kind of iffy. So if you have values that are in the hundreds for absorbance, that is total nonsense. So be careful not to introduce the wavelength value as the absorbance. That's nothing. The absorbance value should be below 1 ideally. In some cases, it might be slightly above 1. That's okay to some degree, but it should not be in the tens or hundreds. Okay, so what we basically do is we solve for the concentration. We add 0.0074 to both sides, that's been done right here, and then we divide by 931.1 to solve for the concentration. All right, so we just plug in the value of the absorbance, 0.220, as shown up here. We carry on with the addition, and then we divide the resulting addition value by 931.1 and find out that the concentration is 2.37 times 10 to the negative 4 molar. Okay, now when you get to this point, it's important to look back at your graph and see if this makes any sense. So we're claiming the 0.220 absorbance is to have a concentration of 2.37 times 10 to negative 4. And if you look at the data table that we have here, where 0.220 is above the third entry, but it's below the second entry. And if you look at the concentration values, 3.54 and 2.18 definitely lie above and below the value that we found. So this makes sense in that regard. So you have different ways of double checking whether your calculations are making sense or not. But this is the type of thing that you're going to be expected to do in this class. So get familiar with plotting graphs in Excel or a program of your choice, and be able to recognize that Y represents something, right? So Y in this case represents absorbance, X here represents concentration, which brings me to the next point. Be familiar with how to plot things on the y-axis and the x-axis, because another common mistake that people make is they'll plot concentration on the y and absorbance on the x, and then they mess up the entire calculation. So something to watch out for. Okay, that's it for this video. I will see you on the next lecture series.